Alright, so we're going to talk about Lewis structures. So this is in the middle of your chapter 6. So Lewis structures are Lewis symbols, and Lewis structures are a little bit different. So we talked about Lewis symbols in chapter 4, but we're just going to talk about the difference really quick. So a Lewis structure is a structure for an entire molecule, an entire compound. And a Lewis symbol is only for an element, and so we place the valence electrons around the element in one per side to give you a little image of what that looks like. Now your textbook will want you to do, or some textbooks want you to do Lewis symbols as the beginnings of Lewis structures, which is why they put that here, but I don't want you to think about Lewis structures and Lewis symbols together until you're maybe a little more comfortable with it, or unless you feel like you look in the textbook and you see the way that they're teaching the Lewis structures. If that makes a lot of sense to you, I can also show you individually if you feel like you need, if you're interested in learning how to do it this way. To me, it's less intuitive for introductory students to take it from the dots all the way into a full structure, because you're not sure if, per se, these two dots here are supposed to remain on this side, or if they're supposed to be put together on one side in a double bond or something. So it's a little harder, I think, for most students to do it that way, which is why I'm going to teach a different way of doing Lewis structures. Okay, so what I do want to look at here is this, in this table in chapter 4, they show you the Lewis symbols for selected elements, and these symbols are helpful to us to look at bonding patterns. And so we're going to look at this table a little bit differently and add some things to it to help us with some typical bonding patterns. So a bonding pattern is the way that the element or the atom in that family finds itself most stable in a bond. And so, for example, we're going to first look at carbon. So carbon likes to have carbon has 4 valence, and in order to make a bond, so let's say if carbon were to make a bond with, let's say, hydrogen, and I'll put hydrogen's dots over here, carbon will say, let's make a bond, and so we're going to be sharing electrons, and carbon will say, I'll share this electron, and hydrogen's going to share this electron, and we make a bond. And we typically will draw a line to show this bond. So every time you see a line, you're going to think that this is equal to 2 electrons shared, 2 shared electrons. And if you see dots, we're going to call this a lone pair. So this 2 shared pair would be called a bonded pair. And a lone pair of electrons belongs only to one element. So, typical bonding pattern and lone pair patterns can go across this periodic table, like the valence electrons will determine that. Now I want to leave alone my metals, because my metals are not going to get involved in covalent bonding for the most part. There are some exceptions, but we're going to be mainly looking at, I'm gonna keep my metals, there we go, my metals out of it. Boron is gonna act like a non-metal, and so you will see boron possibly bonding. Beryllium and aluminum can also bond, but we will typically only use them as metals in this case, and so we're gonna kind of exclude them from this pattern. First of all, you need to know about hydrogen. Hydrogen can act as a metal in an acid, or hydrogen can act as a non-metal and be bonding. So hydrogen has 1 lone pair. So hydrogen can only offer 1 electron in this arrangement. Therefore, hydrogen can only ever have 1 bond attached to it. You may not put any double bonds. You may not put hydrogen in the middle. It cannot have 2 bonds. It can only have 1 line and 1 bond. Boron likes to have 3 bonds. Boron is fine with 3 bonds. These 2 are exceptions to what we're going to talk about as the octet rule of wanting a total of 8 electrons. So we'll talk about that in just a second. So hydrogen likes to have 1 in group 1, boron likes to have 3 in group 3. Carbon is stable with 4 bonding groups, and so those 4 bonding groups may look like this. They may look like a triple bond and a single bond, or they may look like 2 double bonds. So you can have as many different bonding patterns as you can, but essentially carbon does not like to have lone pairs if it can help it, and so it likes to only have bonded electrons around it. For nitrogen family, and this goes for silicon as well, so silicon and germanium as well. For the nitrogen family likes to keep a lone pair and 3 bonded pairs. So you can also write that as a triple bond, or you can write that as a double and a single, still with that lone pair at the top. So as we move down, we get less bonds, more lone pairs. So we start with carbon at 4, nitrogen then has 3 bonded pairs. Oxygen's going to have 2. So oxygen likes to make 2 bonds and keep its 2 lone pairs. And so you can see that this way, or you can see it 1 double bond like this. Can oxygen have just 1 bond all the time? Yes. Oxygen all the time has just 1 bond, which is totally fine. It gives it something called a formal charge, which we're not going to learn about in this course. But you can have oxygen with a 1 bond. In fact, you can have any of these, not this way. What I'm giving you here are typical bonding patterns, and so it's kind of a good place to start to know what looks weird and what doesn't look weird. These are bonding patterns that hopefully by the time you finish all the practice will look normal. And so your halogens over here, they like to have 1 bond and 3 lone pairs, so 1 bond, and then we exclude our noble gases because they don't bond, they're already stable. So that's a typical patterns, and I'm going to take you through the steps from this by looking at what a Lewis structure is. And so here's your textbook kind of giving you these 2 electrons are being shared here, and I don't want you using this dot method because we're kind of it gets a little confusing to have to try to count the dots, and then you're not sure who's supposed to be sharing the dots, how to put them. Again, if you've learned chemistry before and you've learned with the dots, we can work through that. But I find that a lot of intro students get confused with the dots, and so I'm going to show you how to draw these more like this. And so what I want you to do is draw your Lewis structure starting with bonds. If you have 2 elements that are sharing electrons, they have to have a bond between them, and so we're going to start with that assumption and work our way from there. Okay, so again, here's kind of the dot structure, kind of taking you through all the way to fluorine. These are electrons that are being shared. This bonding pair turns into a line. It's a covalent bond. Oh, here's my slide, sorry. So here's my typical bonding patterns that we just talked about in the earlier slide. So we're going to start with the Lewis structure of methane. And what I'm going to do is give you a list of steps in this slide to draw methane, which is a very simple Lewis structure. So first, you're going to count all your valence electrons. So I want you to think about valence electrons as being the total electrons that you have to have in your structure, and so we're going to count the valence for every atom that's in our structure. So I have carbons and I have hydrogens. I have 1 carbon. Each carbon has 4 valence. I have 4 hydrogens. Each hydrogen has 1 valence. So carbon total is bringing 4 valence to the table. Hydrogen total is bringing 4 valence to the table for a total of 8 valence electrons that need to be in my structure. And so when I'm working through, that's where I need to start. How do you know that you're done? How do you know that you've added enough electrons? How do you know how many electrons you have to put in your structure? This is the first step because it's the most important step as far as making sure our structures are correct. So I have 8 electrons to give out, and I have to try to give them out in a way that makes all of the elements happy, or all the elements stable. Next step is to build what I call the bare bones. By placing atom with most bonds. In the middle. And when I say most bonds, I'm referring back to this bonding pattern. So who likes to have the most bonds? Carbon likes to have the most bonds. And so carbon's typically going to be in the middle. If carbon's not around, then nitrogen and phosphorus might be in the middle, or oxygen and sulfur. But typically we're not going to put our halogens in the middle, and we can never, ever put hydrogen in the middle, because it's no exceptions can ever be in the middle. And so by placing the atom with the most bonds, or with the most typical bonds in the middle, we're going to create the most likely common typical structures. And so first thing I'm going to do is say, okay, well, I know of carbon and hydrogen. I cannot put hydrogen in the middle, and so I'm going to put carbon in the middle. And now I'm going to place single bonds to connect atoms. So I know the carbons and hydrogens need to be connected. I'm just going to connect them with single bonds. A note here, try to be symmetrical. So symmetry matters. So you want to make sure that you're trying to put things around in a way that makes sense to symmetry. So here's my methane. Here's my bare bones. And so I'm going to build my bare bones, and then I'm going to count. And so my next step is to count valence electrons and add to outer atoms first. Okay, so I have 8 to give. Let's count my 8. Well, every line is equal to 2. So this is 2, 4, 6, 8. Well, I have 8. And I only had 8 to give, so I have all my electrons in the structure. So I'm going to kind of bypass this third step, add outer electrons first, and then we'll kind of build upon that. But to write down for your notes, add to outer electrons first. You add until you get to an octet. An octet, as you may have guessed, with oct is 8, and so most atoms want 8 electrons, with the exception of hydrogen, boron, and helium. Hydrogen's cool with 2, boron is cool with 6, but you would prefer your atoms all to have access to 8 electrons. And so we add to our outer atoms until they have their octet. Well, hydrogen currently has 2, so it has its octet. So all these hydrogens have 2, and the carbon in the middle has 2, 4, 6, 8, so it's also good to go. Now, to simplify, there we go, count valence electrons and add to our outer atoms first. We always add to the outer atoms first because they're typically the ones that will have some lone pairs and be alright with the lone pairs. Remember, the middle atom is going to be the one that doesn't like the lone pairs as much. And then if you have extra electrons to give, we don't have any here, but you may encounter them. Put them on the middle. And I'll show you some examples of that. Now we're going to check our octet. We just checked our octet. Everyone's got 8, so we're all good. If the middle doesn't have 8, so the middle is missing electrons, erase, and replace. Creating a double or triple bond, and we'll talk about what that looks like. So for your notes, just make sure you have these steps, and I'll be going back over them in class as well, but make sure you have these steps for your notes, and then we'll move on and do some more examples. So, giving you another example, I think, do I have? Yes, so we're going to have some more examples. So here are just some more Lewis structures. You can see kind of how they're collecting the dots and kind of putting them into the bonds, and I want you to use this bond formation a little bit more than I want you to use this dot formation. Actually a lot more. I want you to not really use the dots at all unless you have already learned it that way or you feel comfortable with the way the book was teaching you in that way. But always transform it to this dot, this line formation for me. Okay, so we're going to do an example. We're going to draw the Lewis structure for phosphorus trichloride. So go ahead and try to write the formula for phosphorus trichloride, knowing what you know now about naming chemical compounds, and then we'll draw the Lewis structure for it. Alright, so drawing the Lewis structure here, let's add a page so that I can have a little bit of workspace. Alright, so drawing the Lewis structure for phosphorus trichloride. So phosphorus trichloride is PCl3. It's covalent. 1 phosphorus, 3 chlorine, so phosphorus trichloride. We change that ending to IDE. So first let's count up our valence electrons. Phosphorus, if we look on the periodic table, phosphorus is in group 5, so it has 5 valence electrons. There's 1 phosphorus, and it has 5 valence electrons, putting 5 into play. There are 3 chlorines, and each chlorine has 7 valence electrons, putting 21 into play, for a total of 26 electrons. The second step is to place the phosphorus in the middle, because the halogens do not like to be in the middle. They are stingy, they're trying to look like noble gases, and so they want to be on the outside. So phosphorus is closer to carbon, so we're going to put the phosphorus in the middle here. Now, go ahead and count your electrons. We have 2, 4, 6, so we have 20 left to give. We're going to give outside in. So we're going to give 2 given pairs, 4, 6, and that would be 8 with these, so that's 8. And we're just going to give, I think just giving the outside until it has 8 is a good place to start. So if I know that all of my chlorine has 8, then this is 8 plus 8 plus 8, which is 24. I have 2 more left to give, so I can put it on the phosphorus. So let's go ahead and check our octet. I have 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Here, I'll go back and do phosphorus in a different color so you can see. So for phosphorus, it is 2, 4, 6, 8. And so they're sharing those electrons in the bonds. We can count the bonded electrons for both atoms on either side. Everyone has 8. All my electrons are given out. This is a good structure. So follow the rules step by step. Don't do any double bonding or triple bonding or anything until you think that you have to. So when might I use a double or triple bond? So a double bond occurs when the atoms are sharing 2 pairs of electrons, and it forms when we don't have enough electrons to complete octets. A triple bond's the same way, except we're sharing 3 pairs of electrons. And so going further into an example of showing you that, I'm also going to tell you about how to deal with polyatomic ions. So for your polyatomic ions, the ones you're memorizing, over here we're going to look at this rule. Add electrons for negative charge, remove electrons for positive charge. So if you are negative, that means you have more negative electrons, and so we're going to be adding electrons for negative charge. If you're positive, you lost the negativity, so we're going to be removing electrons for the positive charge. So we look at cyanide. Cyanide is Cn minus. So if we count up our electrons, and let me get this out of here. Let's just go back into our page actually. So if I want to look at cyanide, so building this, cyanide, first count my valence electrons. C, I have 1 carbon with 4 valence, and I have 1 nitrogen with 5 valence, so I wind up with 9 total. Now I have a negative charge. That means I add or remove electrons. It means I add an electron because I have a -1 charge. -2 would mean I'm adding 2 electrons, so I have 10 total to give. Now I don't really have a middle ion here, or a middle atom here, so we're just going to put a single bond between the C and the N. Now we have to decide who gets the electrons first. Who would rather have lone pairs? So the nitrogen would rather have lone pairs, so let's fill up nitrogen first. So 2, 4, 6, 8, and we have 10 total, so we need to put a lone pair on carbon. Now carbon might not like having a lone pair, but it's going to have to do it in this case. And so now looking at my octet, I have 2, 4, 6, 8, nitrogen's good, and carbon 2, 4. Carbon's not good, so I need to back up and I need to do some things here. So I don't have any more electrons left to give because I have 10 in my Lewis 10 in my structure and 10 here, and so I don't have any more left. So I have to erase and replace, make a double bond. So I'm going to erase these electrons and replace them as a bond. Well, now the carbon has 2, 4, 6, and the nitrogen keeps its 8, so carbon's not quite there yet. We need to do it one more time. So let's erase and replace. Now let's recount our valence. I have 2, 4, 6, 8, and I have 2, 4, 6, 8. So everyone has 8, everyone's good to go. This is my structure. One last thing for polyatomic ions. I need you to put brackets around the polyatomic ion with the charge on the outside to make sure that you're very clear that you have extra electrons hanging out in that structure. So to deal with my polys, we're going to put our charge on the outside and put everything in brackets. So there are some exceptions to the octet rule. For example, boron, trichloride, and then the sulfur hexafluoride. Sometimes you have to have more than 8. Like the sulfur right here has more than 8, so 2, 4, 6, 8, 10, 12. Sometimes you have less than 8, 2, 4, 6. If you follow the steps, rule step by step, you'll get it right every time and you won't have to worry about it. Sometimes you're just going to have to have an exception, but if you're not sure, just let me know and I can help you out with that.